welcome to part one of our video on chapter 11.1. Here we're talking about the chi-square test for goodness of fit. And in this particular video, I want to cover how we state appropriate hypotheses, how we're going to actually calculate and compute expected counts for a chi-square test for goodness of fit. We're actually going to calculate a chi-square statistic. We're going to figure out how to do degrees of freedom for this section's chapter and what a p-value looks like for a chi-square test for goodness of fit. We're going to perform a chi-square test for goodness of fit and conduct a follow-up analysis when the results of chi-square tests are statistically significant. Those last two are more hand-in-hand in the part two video, just so you know. So sometimes when we want to examine the distribution of a single categorical variable in a population, so we can use the chi-square goodness of fit test to determine whether a hypothesized distribution seems valid. There's two different tests that we've got here. One's called the chi-square test for homogeneity. I can't say that word right now. And the other is going to be the chi-square test for independence. We'll go further into kind of the nitty-gritty or details of the chi-square goodness of fit test when we get to chapter 11.2. But for today's, we're going to be dealing with just simply the chi-square goodness of fit test and the basics of it. So let's jump on in with an example. The Candyman can. Mars Incorporated makes milk chocolate candies. Here's what the company's consumer affairs department says about the color distribution of its M&M milk chocolate candies. On average, the new mix of colors of M&M's milk chocolate candies will contain 13% of each of browns and reds, 14% yellows, 16% greens, 20% oranges, and 24% blues. Someone took a sample of 60 and went ahead and generated a one-way table to summarize what the counts actually look like in that bag. So in that bag, the blues were 9, orange 8, green 12, etc., etc. So we notice that if we look at the p-hat value, the proportion of blue candies in this bag, 9 out of 60 is only 15%. And they clearly told us, the Consumer Affairs Department said that the distribution should be closer to 24%. So we're asking ourselves, is something fishy going on? Well, in the past or in the previous chapters, you might have tried to use a one sample z-test for a proportion to test the hypothesis. So your null would have been that p is equal to 0.24, and your alternate is that p is just not equal. It would have been a two-sided test. And p is just that population proportion of blue M&Ms. But if that's all we're testing is the blue M&Ms, what about the remaining colors? Well, then that seems pretty inefficient. You've got to do a z-test for each and every single category. And what if you've got more than just 6 categories in a future experiment? That just seems like a lot of work, and it just seems chaotic to deal with so many different comparisons. So instead, they have the chi-square goodness of fit test. So instead of performing one sample z-test for each color, because it's not going to tell us how likely it is to get a random sample of 60 colors or 60 candies with a color distribution that differs as much from the one claimed by the company as this bag does, then we have to use this new significance test. So in our example, our null hypothesis for our example would be the company's stated color distribution for M&M milk chocolate candies is correct. So guess what the alternate is going to be? Isn't that correct? And this is a pattern that you're going to develop for all of your chi-square null and alternate hypothesis. It's simply going to be the information in context is correct. The information in context is not correct. It does not have a specified distribution. So if we actually write out for our example, our null hypothesis would be that these are the distributions of those colors, 24%, 20%, 16, 14, 13, 13. And then the alternate is that at least one of the percent values for these colors is incorrect. When we are talking about chi-square goodness of fit tests, make sure that you recognize that we are comparing observed counts from their expected counts. And I'm going to keep on saying that word counts, because a big mistake that kids make is when they're doing a chi-square, at some point they start using proportion values instead of the actual numbers, the quantity, the counts. So make sure you're not making that mistake. But the more observed counts differ from the expected, so the more that distance grows between what you've actually seen in your sample versus what the company or whomever is claiming, the more evidence we have against the null, the more likely we are to reject the null hypothesis. So, assuming that the color distribution stated by Mars Inc. is true and that 24% of all M&M milk chocolate candies produced are blue, for our random sample of 60 candies, the average number of blue M&Ms should be 14.4, right? So I took the 24% and multiplied it by my sample. In my sample, I should have pulled out 14.4 blues to get that 24%, or somewhere near that line. So that becomes our expected count. We can do the same math to find the rest of the expected counts. Ta-da! So now I'm going to create a little table where I'm going to look at my observed, so what I actually saw in that bag of 60 versus the expected, which we just calculated for ourselves. A big important number to remember when we're thinking about expected counts is the number 5. As we are doing a significance test, you know that at some point I'm going to talk about meeting conditions. And you have to meet the condition of 5 or higher in order for chi-squared to meet the large counts or large proportion value, large numbers condition. Oh my gosh, couldn't speak for a second. And if you notice our expected counts, not a single one is below the number 5. So we're good in that section. We'll keep on talking about conditions as this slideshow goes through in this video and in the next. To see if the data give convincing evidence against the null hypothesis, we compare the observed counts from our sample with the expected counts, assuming that the null is true. If the observed counts are far enough from the expected, that's the evidence that we're seeking, so we can reject the null hypothesis. So if we look at it visually, can we really say that there is a distinct difference between the observed and the expected? That's not enough for us. So we could maybe notice some things. You could read through this little paragraph for yourself to see. But the bigger thing we need to do is actually use the chi-square statistic. So formula coming up. Boom, chi-square statistic. It is a measurement of how the literal distance that is occurring between the observed counts and the expected counts. And so just to break this down, chi-square or x squared is going to be equal to sigma, the sum of all of your observed minus expected squared divided by expected, plus next observed minus next expected squared divided by next, et cetera, et cetera. So here's our information. Let's plug it into our formula. Following the color, you'll be able to match them up. Boom, boom, very nice. Now I add them all up together and I get 10.18. But what does that mean? X squared, chi-squared is 10.18. Well, we need to actually do a little bit further analysis. You can read through this little paragraph on bottom, but in essence, what it's saying is a large chi-squared is rejecting the null. A small chi-squared is consistent with the null, so failed to reject the null. But when do we know what's big and small? We really can't just say. We can't just be like, okay, 10.1 big. There's no value for that we recognize. So we actually have to reference our chi-square distribution. We get to use our chi-square distribution, or table C in the back of your textbook, I believe. We get to use that when your expected counts are all at least 5 or higher. And we did pause and check that. Our expected counts were 5 or higher. So we're going to use our chi-square distribution. Just a note, this is also talking about just the general properties of chi-square distributions. They are never going to be, they're not normal. They are right-skewed distributions, and if you want, you can check the math on it, and it's because they will always be positive because the numerator is always squared. So looking at our example, our chi-square statistic was 10.18. Well, we need to know our degrees of freedom. If we're just talking about chi-square as a goodness of fit test, our degrees of freedom is simply the categories minus 1. With t-value, degrees of freedom was n minus 1, so this isn't very hard. Categories minus 1. With our candies, there were 6 color categories, so 6 minus 1 becomes 5. So our degrees of freedom is 5. We go to our chi-square distribution with degrees of freedom 5. We look at table C, and we come on over, and we're going to find a value under row 5, because that's our degrees of freedom. We're going to find a value that matches closely to 10.18. So we're right here in between these two values. So if you look at those p-values, we're not at 0.10 and we're not at 0.5. We don't know our specific number, but we sure know that we are between 0.05 and 0.1. And since that's greater than 0.05, we must fail to reject the null. Because remember, when our p-value is bigger than alpha, we fail to reject. When our p-value is less than alpha, we reject the null hypothesis. So what does that mean in context? If I fail to reject the null, then that means I'm agreeing, but not really, because we don't use that word. We're agreeing with the null hypothesis, or in essence, what's the better way to say it? We don't have sufficient evidence to conclude that the company's claimed color distribution is incorrect. We're not going to say we agree with the company's claimed color distribution. We don't use that word, but we are going to say that we don't have enough information to say it's incorrect. And that is it for chapter 11.1, part 1. And I'll see you for part 2.